Pittsburgh University, 2021. Okay, great. So the agenda is to both introduce you all to a little bit of coding theory and at the same time prove two very recent algorithmic results. The challenge is doing it all in 3 or 4 lectures, and I'm going to try to do it by maintaining an aggressive pace. I will go fast, slow, fast over the basics and slow over the new results, and then fast again over the basics, and then slow over the newer result. Or maybe not so slow with the latest of the results, but I'll try to prove all of these results. So today, mainly to tell you about the basics of coding theory, and hopefully I'll at least be able to tell you what the goal is for the next lecture and give you a little bit of a sense of what we're going to do in the future. All right, so the error correction problem is the problem that we will be dealing with in these lectures. It's an old problem. It started in the 1940s when people started building digital communication devices, digital computers, and realized very quickly that when you're transmitting digital information, noise can be make things very unreliable. So a message of the form "we are not ready" can get communicated as "we are now ready" and completely change the meaning of what you intended with just one single error. So the meaning changes discontinuously as a function of the distance. So a number of errors is tiny, but the meaning of the message has changed. So we cannot afford these changes in digital information. So we need to correct them. How shall we correct them? 2 seminal works studied this. Shannon's work in 1948 and Hamming's work in 1950. Shannon was interested in a broad overreaching theory of communication, more than just error correcting codes, which is all we will talk about. Hamming was the one who actually introduced the theory of error correcting codes. It's error detecting and error correcting codes, in case you can't read that. But together, the two set the frameworks of the field, and this is what we will be studying today. Okay, so Shannon, how did he model the problem? What is noise? How do you model noise mathematically? Shannon said, okay, it's basically noise is just going to change letters of the alphabet randomly. So noise happens out of a pure random process, no maliciousness involved, nobody coming in knowing what you're planning to do to correct the errors. They just make errors. So it's a very simple example, and this is going to be the example we'll focus on in lectures 3 and 4, is the binary symmetric channel with some parameter, let's call it epsilon today. On this channel, you can transmit a 0, and the receiver will receive a 0 with high probability, let's say 1 minus epsilon. But with some probability, it'll get flipped and you will see a 1. If you send a 1, the receiver will see a 1, again with probability 1 minus epsilon, but might see a 0 with probability epsilon. Epsilon can be any number for this lectures. It could be something, between 0 and 1. 0 to something greater than 1/2 is kind of weird, so we will not really talk about it. Strictly less than 1/2, all of these notions make sense. If I send you a 0, you will see a 0 with higher probability than you will see a 1. But it could be, whatever epsilon tells us it is. Can you communicate with this channel? Hamming asked a different kind of a question. He modeled the noise as if it's adversarial. So somebody who comes in and knows the entire system, knows exactly how you're planning to recover from errors, will change the letters. So you could be transmitting not necessarily bits, but any sequence of letters from some alphabet called sigma. Sigma will be a finite set for us, and that's all we will have as a restriction. You send n letters over this channel, the receiver will get n letters over the same channel, but they may not be the same letters. What will happen is some letters are going to get changed. How many letters? This is all that is bounded. The assumption is this channel can change, say, 20% of the letters that you send. And if that's the case, then you can get any symbol any sequence which differs in 20% of the characters. So if you have some n bits that you're transmitting, x1 to xn, n letters of an alphabet, what you will receive might be some other n letters. How you measure the distance between them is simply the number of coordinates where things change. How much do they change by is not important to us. Just is it the same coordinate or is it not? Okay. So if we are sending, English letters, we are not ready, and we get the symbol sequence with now over here, then that was one letter. That's delta of xy is 1, capital delta. We will often study little delta just because, if I send you longer sequences, I should expect more errors. So we will often normalize this by saying, okay, if we are sending n things over this channel, then let's divide it by n, and that will tell us how many errors we are allowed. So Hamming said, suppose the channel is capable of changing epsilon fraction of the symbols, in the sense, if you send x, you will receive y, such that delta of xy, little delta of xy, is at most epsilon. How do you deal with this kind of a channel? Okay. Now, how is this error introduced? Well, somebody who knows what you're planning to send, somebody who knows how the error correction and error recovery methods work, everything is known to them. They're going to introduce the changes, but we still want to deal with epsilon fraction of errors. Okay, how much errors can we deal with? Okay, so these are the two notions, and based on these two notions, Hamming, adversarial errors, arbitrary, no assumptions on how the error patterns are. Shannon, simple, random, every bit is independently flipped. These are the two settings. Can we correct errors in these two cases? Okay, that's going to be the problem setup, and we will start looking at some solutions now. Okay, so in order to define the solution concept, there are three concepts I want to mention: the encoding, the decoding, and the code. So let's start with encoding. So the natural thing to do is, once you have a message in hand and you know that the channel that you're using is noisy, you expand the sequence, include some redundancy symbols, include some checksum maybe. The oldest classicalist solution was you repeat the message several times. Every bit you want to send, you send it 20 times. And then the receiver will look at these sequences and take the majority over every block of 20. These are things that you could do. We don't want to restrict you in any way in what you want to do. All we will ask is, okay, how do you decide to go from k letters to some n letters where n is larger than k? Okay, typically much larger, but n is at least larger than k. So we will ask you to decide, and that is determined by this function called the encoding function. The decoding is determined by an inverse map, which takes long sequences and sort of is tolerant of the errors that the channel might have introduced. Is going to try to recover from them, and it will try to produce back a message, which was what was sent. Okay. And our desire will be, after you've encoded a message and the channel has done its nastiness, it has introduced errors, your decoder is still able to somehow recover the original message. So recall, we do not care. We are not happy if m and m prime only differ in very few coordinates. That's no good. We do not want we are now ready to become we are not ready, or vice versa. Okay. So m, if you transmit m, the receiver should know m. That's the guarantee we want. Later, we will relax it in some ways, but think of it, this is what we want. If the channel happens to be probabilistic, we would want it to happen with high probability over the channel. But if it's adversarial, then we would want this guarantee deterministically. We want it all the time. Okay. And this is what we want to design. Really, the encoding and decoding are all that matter to us. Okay. Of course, we will want encoding and decoding to be efficiently computable functions. So you are given k letters over some alphabet, you should run in time polynomial n k and the size of the alphabet. But it turns out that it's very interesting and useful to study what kinds of n letter sequences are produced by this map E. Okay. So if I range over all the possible messages, this is what I'll call a message. This will be the encoding of the message, or space of encoding of the message. So sigma to the k, any element of that is a message. If I'm taking a message and I encode it, what is the set of n letter sequences that I reach? Okay, this is called the error correcting code. Okay, ideally, so for instance, if we use the repetition code, I repeat every symbol 20 times. This sequence will only include things which have every character repeated 20 times. Okay, n will be k times 20, and you will have only those things. We would like to understand what structure of the code might make for a good encoding and decoding scheme. So these are allied related quantities. They are not exactly. Okay. Now there was a question in the chat. When we say with high probability, do we mean probability 1 over polynomial in the m right now, by the way, is not an integer. It's a message. M is an element of sigma to the k. When we say with high probability over the channel, you could think of probabilities like 1 in n squared. That's okay. We will also be very happy with probability which is just tending to 1 as n goes to infinity. So 1 over log n is okay. At the same time, most schemes that we know achieve 1 in exponentially small in n. Okay, so 2 to the minus 0.01 n can often be achieved. Great. And so those are the numbers that we will be happy with. We'll talk about this more precisely later. Often when we'll say, oh, things are not possible, it'll rule out much weaker definitions of possible. When we say things are possible, we will achieve very strong definitions of possible. Great. Keep the questions coming. So there are many possible encoding and decoding schemes. How do you choose among them? We want to be scientific about it. So 2 precise measures which pretty much dictate what we want. Okay, the second one is not going to be well motivated right now, and honestly, it's not well motivated, period, but it's a quantity that we will often pay attention to. The rate of the code is certainly very important. I can repeat every symbol 20 times, and maybe I can correct 5 errors out of it in an entire transmission. That may not be very useful. Okay, what we would like to do is minimize the amount of redundancy that we put in. If I have the channel, I want to put in as much real information into it. K should be as large as possible because I'm using it n times, and I want k over n to be as large as possible. So this is called the rate of usage, rate of the code, rate of the code, rate of the encoding scheme. I will not be distinguishing between these at all. The message length, k divided by the block length n. Clearly, we want this to be as high as possible. A second thing that we will be interested in, at least initially, just to give us some sense, is distance. If the code happens to have lots of sequences which are very close to each other, at least in the Hamming sense, when the adversary is introducing errors, they can take us from one valid code word to something completely different by introducing very few errors. So we would like the code to have large distance, where the distance of a code is defined as the following quantity. You look at any pair of code words, any pair of things that are encodings of 2 different messages, and you look at the minimum distance between them, at the distance between them. The distance is again the Hamming distance. How many coordinates did I have to change to go from one to the other? Okay. And as usual, capital delta will be for non-normalized quantities which are integers between 1 and n. Delta of C is going to be normalized so that it's now in ratio, it's between 0 and 1. Often looking at things between 0 and 1 and taking the limit as n goes to infinity gives us a lot of the insights. Okay. So the 2 parameters of interest, the relative distance of the code and the rate of the code. What we would like, everything. So what I would like is the following. So if I want to plot rate versus distance, what would I like? I would like to be here. Okay. Rate of the code should be 1, maximum possible. The distance of the code should be 1, also maximum possible. Hopefully, some math will tell us that this is not achievable. So then we will try to get as close to whatever it rules out. Okay. What can we do right now? Let's make sure that we understand the definitions. This is possible. Okay. This point has rate 0 and relative distance 1. How do you achieve rate 0? You have only one message, which is all zeros. There are no other messages. So there is nothing that I can actually communicate, because even before I send anything on the channel, you know what I can possibly send. There's only one code word. On the other hand, it's great as far as errors are concerned. No matter what channel does, you will never get the message wrong. It's just that it's not any use. Okay. So this is achievable, but not very useful. Here is something else that's also achievable, rate 1 and distance 0. Here I just take encoding to be the identity map. Okay, k equal to n. Every sequence is sent exactly as it is. Since there are no errors, there's no problem with this encoding scheme, and you can get n symbols of message out of n uses of the channel. So the rate is 1, thing is 0. So these two are possible. And what we would like is this, and we would like to know if this is achievable. Okay. So let's start with our first proof of the day. It's not achievable. This point is not achievable. In fact, much more is not achievable. It's a very simple, it's called the singleton bound. Singleton is the name of a person who published a paper with this bound. The bound is basically the pigeonhole principle. Okay. So suppose there's an encoding function which maps k symbols to n symbols. The claim is that if you look at the non-normalized distance of the code, k plus that distance is at most n. There's a +1, but let's ignore it for now. +1 is negligible. Okay, k plus delta is at most n. If you relativize it, divide it out by n or n plus 1, whatever, you get rate plus the distance is at most 1. So on this picture, it translates to that line. Okay, this is the best you can achieve. No codes here. Okay, so let's see how we prove this. It's very, very, very simple. So suppose you give me a code, E maps k symbols to n symbols. Let me project every n letter sequence to the first k minus 1 coordinate. So just take any sequence you give me, x1 to xn. Let me just send this projection x1 to xk minus 1. Okay, just look at every sequence restricted to the first k coordinates, k minus 1 coordinates. Well, when you compose pi with E, what do you get? Well, you apply sigma to the k to sigma to the n by E, and then go from sigma to the n to sigma to the k minus 1 by pi. Then you get some function. Clearly, this function has a larger domain than the range. So there must exist 2 points in the domain which map to the same point in the range. So what happens if there is x and y such that pi of E of x equals pi of E of y? Well, that means that when I look at the first k minus 1 coordinates of the encoding of x, it agrees with the first k minus 1 coordinates of the encoding of y. Okay. So where can x and y disagree in their encoding? Well, these parts are equal. So this is where they are not equal. And how many coordinates do we have here? It's n minus k minus 1. Okay. That's this proof. That's this bound. Okay. So obviously it's completely trivial. So whenever I teach this lesson, students say, okay, so let's improve this. Okay. First thing you want to do is let's improve this bound. We didn't use anything, right? Can you really not do anything better? So let me actually tell you about one family of codes that I have. It's an encoding function. It's called the Reach-Solomon codes. And what's these codes? These are codes defined over alphabets which are a finite field. If you're not familiar with finite fields, just think of working with integers modulo a prime. Okay, so think of q as a prime number, and you're working with addition, multiplication modulo this prime. We will pick this prime to be large, larger than our n. So actually our alphabet is large, but we never assumed that our alphabet was small. This proof works for any sigma k and n. Okay, so let's work with large alphabets. And the parameters of the code will include in this FQ, which is a field with exactly q elements, pick n distinct elements. You can obviously pick n of them distinctly because q is larger than n, so there are n distinct elements. Let's fix them. This is now designed our code. We have designed the code. We are going to go off. And now I get a message and I have to send it to you. What is a message? Message is going to be k letters of sigma, which is k letters of FQ, the field on q elements. And I think of these messages as being the coefficients of a polynomial in one variable whose degree is k minus 1. Okay, so that polynomial is given by summation m sub I x to the I. Okay, it's a very abstract algebraic object. It is not, don't think of giving concrete meaning to it yet. It's an abstract object, and I want to send this very abstract object to you. I can think of two ways of sending it very naturally. One, I can send you the coefficients, and you will know what this abstract object is, but that's no use because I just created this complicated map which said, oh, let's take polynomials and so on, and then went back to sending m0 to mk minus 1. That wasn't interesting. But we know that polynomials can also be specified by their values. So why don't I send you m of alpha 1, m of alpha 2, and so on to m of alpha n? Now, if n is greater than equal to k, evaluations of a polynomial of degree k minus 1 at k places uniquely specify the polynomial. Not only that, you can actually do the interpolation, Lagrange, Newton, whatever, and you can actually find the coefficients given the evaluations. But I'm using n actually much larger than k, n maybe twice k. So there is a lot of redundancy here. There is extra information. How useful is this extra information? Turns out it's extremely useful. And so this is our encoding. So now I have completely specified the encoding. And here is an exercise. As with most of this lecture, I will not do the exercises. I will tell you when they are. And you should all go do the exercises offline when you get a chance. Okay. And that way you will know whether you are following the lecture or not. So based on the fact that if I take a polynomial which is not 0, and it has degree k minus 1, it can have at most k minus 1 roots. We know this. Based on that fact, it follows that the Reed-Solomon codes, if I take two different messages and I encode them, they disagree in at least n minus k plus 1 places. They agree in at most k minus 1 places. When two polynomials agree, their difference has a root. Their difference is a degree k minus 1 polynomial, and if the two polynomials are distinct, this is a non-zero difference. The non-zero difference cannot have k minus more than k minus 1 roots, so it follows that this holds. So what is the moral of this story? We have codes which match the singleton bound. We said this is the best you can achieve. Here we have achieved it. Okay. So, okay, great. I think this is a good point for me to pause and look at the chat to make sure that, yeah. So Lee asked, is pi a decoding function in this thing? No, pi is just an arbitrary function used to make this proof work. Okay, so this was just a simple function project to the first k minus 1 coordinates. It tells us how to prove that the distance is small. Okay, great. I think Rani's answering that. Yeah, great. Any other questions at this stage? Okay, so
what happens if we change the length of the code?
If you change, so notice you can take any n you want, and you can make n larger, smaller, and the Reed-Solomon codes work, provided you don't try to make n larger than q. What happens if n is, you want to fix q and make n very large? I don't know when I'll talk about it. I will talk about it sometime. Is that the question, Anika?
Yeah, it is.
Okay, so we will try to do something. So, but so few things. So okay, good. So there is this warning. I think this is related to what you said. Oh yeah, right. But these codes only work up to a certain q, up to a certain length. If you want to work with a larger length, you have to work with a larger alphabet. And so you have to sort of design the code and the alphabets together. And one thing I want to say as a message is that this is actually completely okay. So maybe, okay, good. I think we are going to get to that question now. Okay, great. So what happens if you wanted to work with smaller alphabet size? Okay, it's actually pretty easy to prove that there are pretty good codes. What we achieved was, on this picture, we got to this line. Okay, this line is great, but that line you will actually get to only over q, which is very large. I will not quantify this answer, but you'll get close to this line only by using large q. But you might say, okay, look, I know how to get over large q on this line. How about q equal to 2 in this point? Can you get something slightly positive delta, slightly positive r, but over small alphabets, q equal to 2, 3, 5, etc.? And the answer is yes, you can get any of those. So these are a collection of exercises today. The first claim, and which I won't prove, but they're not fundamental, but it's always good exercise. If you haven't seen these and done these before, it's a good idea to try them. You can pick whatever delta you want, which is positive, and there exist codes whose delta is at least that quantity that you picked, whose rate is at least that quantity that you picked. So there exists some positive rate as long as you're asking for relative distance which is less than a half. And the exact formula is here, but we will talk a lot more about this formula in a couple of days, so I won't dwell on it today. And how do you prove that such codes exist? You pick this code as random. Amongst all the existing codes in the world, pick one uniformly. So for every message, pick the n-letter sequence randomly. You can analyze what this is expected to do with high probability, and then that implies in particular that such a code exists. I will not prove this particular theorem. Ignore the red part when you're doing the exercise, but at least try to prove that you can always get some positive rate and epsilon. Okay, so in fact, this theorem is saying, the existence is saying on this picture that you can get some line that looks like this. Okay, it's not clear exactly what it proves, but something along these lines you can always, sorry, actually it says something like this is always doable. Nope. If you have 1/2 here, it says something like this is always doable. And you can go all the way here. Okay, so everything slightly positive, but you can get it. Great. The catch with this is not explicit. I don't know how to build this code. If I had to encode and decode, I could build I'd have to prepare a huge table of size 2 to the k. And then when you say, okay, I want to encode this message, I'll do a table lookup. So short of an exponential space and time algorithm, I don't know how to do this any better. If you want to do this slightly more cleverly, efficiently, you can do the following. For those of you who know what a Toeplitz matrix is, pick a random Toeplitz matrix and use that as your encoding function. So if you have, so the matrix will look like this, and you multiply it by x, and that's your encoding. So this is your matrix T, and Toeplitz means that entries on all these diagonals are the same. Okay, in any one of these, if you follow this path, it will have the same entry. Okay, so if you pick that kind of a matrix at random, then it will actually achieve as good performance as what we did in part 1. And now comes the very neat idea, the idea of concatenation. And it says that if you take Reed-Solomon codes that we talked about over large alphabets, combine it with some code that you know exists, you get a much more explicit code. What does it mean to combine? So what is a Reed-Solomon code? It takes letters of FQ and maps them to FQ, K letters over FQ, and maps them to N letters over FQ. Okay. In our thing, we'll say, let's view elements of FQ as some binary strings. You could pick arbitrary binary string representation as long as, Q is smaller than 2 to the less than equal to 2 to the T, you can represent it. Now what we will do is view the Reed-Solomon code as saying somehow, let's assume that these are exactly equal for this line. So we have a way of taking sequences of K letter strings where each element of the sequence is itself a T bit string. And since we have a map which takes elements of FQ to elements of FQ to the N, we will now get T bit sequences and N such T bit sequences. Okay, so pictorially what we've done is there is T bits here and so on. So there is 1, 2, and so on up to K such things. The upper encoding Reed-Solomon says, oh, how do we take this and produce new sets of T-bit sequences? And there are N of these. Okay. Now, firstly, this is a binary code already. I mean, I'm telling you how to go from TK letters to TN letters. Okay, you just have to do the brackets differently and then you get it. But it's not going to get us such good performance. It's not actually going to be above the, it's not going to be to the strict right of the y-axis in this picture that we are drawing. So to make it better, what we will do over here is put another encoding function, E2, which will take these T letter sequences to L letter sequences, where L is larger than T, and just apply it blockwise to each block. Okay, so I get N such sequences of L letters each. And what's the feature that we have? Well, most of these, if I start with 2 distinct messages, most of these coordinates over here will be different. Most of these blocks will be different. For 2 blocks which are different, if I look at this thing, a constant fraction of these symbols will be different. So when you put the 2 of these steps together, you get the 2 distinct messages are mapped to binary sequences which differ in constant fraction of the symbols. All I need is a good encoding function called E2, or this E inner. How do I get this E inner? Well, let's go and look at this theorem and apply it. Why is it applicable now when it was not previously? Well, here I had to do a random search. I had to go over a space of 2 to the n possibilities and figure out what it is. The 2 to the n has now become 2 to the log n, 2 to the order of log n, because I'm only looking at, I only need to find a code which will map order of log n bit messages to order of log n bit encodings. I can search in the space in time polynomial in n. So moral of this story, so this was a very quick thing, and here is an important, again, this is an exercise. So please do try this. If you do what we claimed above, the relative distance of the 2 codes multiplies, the Reed-Solomon code and the inner code. The rate also multiplies. Since both of these are quantities less than or equal to 1, multiplication is not necessarily good, but still, if they're positive, they'll remain positive. If both of these quantities, if all 4 of these quantities were positive, if these quantities are all positive, then these 2 are positive. So this is very explicit, and it also tells us, look, actually working with large alphabets is not a bad idea. It's a great way to get codes over small alphabets also, and we can to the thing. So somebody's asking, can you explain the encoding again? Absolutely, great question. This is the kind of question that I think is worth it. So what are we doing by the encoding? We're taking one outer code, which is called the reach, which is a familiar Reed-Solomon code. It actually mapped FQ to the K to FQ to the N, but we are saying FQ is 0, 1 to the T. We've somehow managed to find a field of size exactly 2 to the T. They do exist, and those are the ones that's best for this example. So such an encoding is already telling us how to take K sequences of T-bit strings and map it to N sequences of T-bit strings. So that's this encoding. Take K sequences, each one is T bits long, and map it to N sequences, each one is T bits long. Now I'm going to take a second encoding scheme, which takes T letter sequences and maps them to L letter sequences. L is larger than T. Now, because I'm going to work with Q, which is roughly N, log T, which is log Q, is roughly log N. So I only need to deal with log N bit messages over here. So this is a code that I can search for exhaustively. I run through all the possible codes, find one which works, and use that. And now having used that, I just use it for each coordinate. This is E in of the first block. This is E in of the second block. This is E in of the last block. Okay, so that's the composed code. And if you use this code, then you get these two properties. The inner code's rate and distance are here. Reed-Solomon's rate and distance are here. This is the combined code. Okay, great. Questions? Okay, so this is, so codes over large alphabets are good enough for us. And in fact, that's what we're going to do. When we don't care about the alphabet size, we will use alphabets at most thing. Rani is asking a question. Are you still limited to rate at most 1/2? Yes, the inner codes, if they're going to be for binary alphabet, the rate will be at most 1/2. If you're working over codes over larger alphabet, we can get higher distance and rate. Okay. Rate is not 1/2. Rani, the distance of the inner code is at most 1/2. The inner code could have rate close to 1. We didn't prove it over here, but they do exist. Okay, great. So now I've told you that this is how you can get good codes with good distance, but what does distance have to do with error correction? We want to correct errors. Let's get back to that question. And well, Hamming gave us a partial answer. He said, well, if you have a code whose relative distance is delta, then it will actually correct delta over 2 fraction of errors. Okay, and the rough idea is very simple. Hamming distance has the triangle inequality. If I look at this distance from x to y, it's as small as the distance from x to z plus z to y. Why is it helpful? Suppose I start with a message. Let's start with a message M, transmit it. So maybe it became, after encoding of the message, I get some sequence X. The noisy channel acts on it and changes arbitrarily less than delta over 2 fraction of the error coordinates, let's say. And so I get some Z, which is delta of xz is less than delta over 2. Okay. So suppose you claim, oh, this could have actually, I mean, how do I want to go back? Well, I look at Z and I look at all the code words nearby and see which one is closest to it in terms of this distance. I claim X is unique with that property. Why? Suppose there is some other message, M prime, and its encoding of M prime is, let's say, Y. Suppose it turns out that this is also satisfying delta of zy less than delta over 2. What do we have? We have the distance between these two is less than delta. And this is the encoding of M, that's the encoding of M prime. This violates the definition of our code has distance at least delta. Okay, so given Z, at least existentially, the algorithm for decoding is clear. I mean, non-constructively, non-efficiently, algorithm for decoding is clear. Look at all the possible messages, look at all their encodings, find out which one is at a distance of less than delta over 2 from the received sequence Z. That is what we want to use. This picture is good and bad. It tells you that you can correct delta over 2 fraction errors, but it seems to suggest that delta over 2 is the maximum fraction of errors you will be able to correct. You know, if indeed m and m prime satisfy this distance is equal to delta, then I can use over here a Z which is exactly midway between the two. Okay, so let me redraw the picture over here. So let's see if I can do this. So suppose, let's assume that on this part, X and Y are equal. Okay, so these parts are equal and these parts are unequal. Okay, now what can I make Z look like? I can make Z look like X and Y, both of them here. And then I can take this portion and copy it here. I can take this portion and copy it there. And now the received Z is exactly halfway between this sequence. So the received Z is exactly halfway between these two. So if you actually receive the sequence, you cannot tell whether you came from X or you came from Y. Okay. So for the longest time, we used to think that, okay, that means the maximum fraction of errors that you can correct with is half the distance of a chord. And the distance of a chord is some number between 0 and 1, okay, even over large alphabets. So the maximum fraction of errors you can correct is 1/2. Okay. Now we decided, in the last 20 years, we've figured out that, oh, this is not the right objective function. Unique decoding is not, should not be our goal. You have a DVD, it's got all your family photographs from 30 years ago, and it's scratched up miserably. You can go to two different vendors. One of them says, look, I have this thing is not uniquely decodable. The other one says, look, either this DVD is, this DVD should be corrected to either this sequence or that other sequence. The second store is obviously doing a better job, right? I mean, if one of those two is the right answer, then you're pretty happy. You have your family photographs. So list decoding says, let's go for a weaker notion of decoding, which says if the number of errors is too much, then we will accept a small list of possible code words, provided one of them is the actual code word that we care about. Okay, so let's define that formally. So in English, it just basically says what I just said. Let the decoder output a small list of code words, and success is defined as saying list includes the transmitted code word. Mathematically, what we're going to say is encoding is still the same, map k letter sequences to n letter sequences. Decoding definition is n letter sequences get mapped to a set of k letter sequences, a set of size L. I will call it a sequence of size L, but really it should be set is the way I'm thinking of it. The ordering within the sequence is irrelevant. So there are L elements of the sequence that we are outputting. And we say that it is correcting epsilon fraction errors using lists of size L. That's already baked in here. What does it mean to correct epsilon fraction of errors? If I sent a message M by encoding it, and the received sequence was Y, which had epsilon fraction errors, at most epsilon fraction of errors, then when I apply the decoding, M is included in this thing. Okay, does this make sense? This is a central definition for what we want to deal with in the rest of this lecture and the next lecture. It simply formalizes what we said. You transmitted the encoding of a message. You received something which had epsilon fraction errors. When you applied the decoding to what you received, which is the y, your message is included in this list of size L. Okay. And this is called algorithmically, I mean, we'll say this is algorithmically less decodable if encoding and decoding are all polynomial time computable. Okay. So this is the definition that we want to work with. And we would like to say, what can you actually, what kind of errors can you recover from? Okay. So let's look at the limits of error correction, what's achievable and what's not. So just, Dmitry, I should go on till exactly the half hour.
Well, yeah, if you want, but you can leave some time for questions.
Ah, I see. I mean, questions after the half hour is too late. Okay, let me keep going and then we'll see. Okay, great. Okay, so limits of error correction, what's possible? We know based on the distance thing, we should not be able to get distance better than this line, right? I mean, this was the singleton bound. If half the distance is all you can achieve, then if you are using a particular rate, this is the amount of errors that you'll be able to correct. Half, this line is 1/2 of that line. Okay. But we are saying let's allow list decoding. So maybe we get some curve that looks like this. What can we get over here? So where is the list decoding curve here? And what can you do algorithmically? So the goal from now on in the next couple of this lecture and the next is to basically get very, 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 very close to that line algorithmically. So we will have both codes and decoding algorithms. Since we're going to do both codes and decoding algorithms, what I'm going to do today is very quickly tell you about how to list decode, read Solomon codes. It will not get us to this line. It'll get us something like this. Okay, something much weaker, but it'll actually get close to here. It'll actually correct more than 50% errors in some ranges of the cases. But most importantly, it's a very simple idea, which will also be very useful in the next lecture. So I will tell you about how to list decode, read Solomon codes. Okay. All right. So that's the goal. I think this is about 2 slides worth of material. Yeah, 13 to 15 it says. So 2 to 3 slides worth of material. So this is what we're going to do. Questions before we launch? All right. So very quickly, the decoding problem is very, very easily stated. It's, you don't have to remember all of this lecture to remember to figure out what the question is. The question is very simple. I have some finite field. I have these parameters n and k. I have some values alpha 1 to alpha n that we fixed. And we transmitted something polynomial evaluated at alpha 1, polynomial evaluated at alpha 2, etc., etc., etc. What we got was beta 1, beta 2, and so on to beta n. Obviously, there were errors in the transmission. That's why it's not p of alpha I, it's beta I. What we want to find is that polynomial p, which satisfies that when I look at I such that beta I equals polynomial at alpha I, this amount is, if this number is large, it's at least 1 minus epsilon times n, then I want to find p. I want to find all such polynomials. Okay. So this is an algorithm that I came up with in 97. So it's, I think, very simple. I'll explain it for some special range of the parameters, but this is the whole algorithm. Okay. So what's the general idea? It's very hard to pose an algebraic. This is an algebraic question, except for the fact that, there is combinatorics here. There is a set which is defined and the set needs to be large, and it says on the good set, you should do X, on the other set, I don't care what you do. It's very hard to explain, to explain the data, the input, when you have this, this partial results. What we will try to do is find one explanation which will explain not some subset of the data, but all of the data, all the alpha i's, beta i's. How are we going to define it? We explain it. We're going to find some polynomial q such that q of alpha I, beta I is 0 for all I. for all I, 1 to n, every one of these points, alpha 1, beta 1, so on to alpha n, beta n, they're all going to be zeros of this polynomial. I will, of course, insist that this polynomial is not identically 0. Okay, so not all the coefficients of Q are allowed to be 0. It's easy to find a polynomial which has maybe degree n in x and 1 in y, which has this feature. Okay, y equals f of x. May also be moderately easy in many cases to find a polynomial whose degree is n in y and 1 in x, which has this feature, x equals f of y. Maybe that'll work out. What we'll try to do is do the trade-off. And the trade-off is, interestingly, it's not the arithmetic mean, it's the geometric mean of the two numbers. We had 1n as a possibility, n1 as a possibility, but you can also do square root of n, square root of n. Why is this? Okay, we'll talk about it in a moment, but this is what we're going to do, and we're going to find this polynomial. Once we find this polynomial, we will just, this is a polynomial in 2 variables. We apply factorization algorithms, and factorization of polynomials is very well settled. If it has any polynomial factor of the form y minus p of x, that p is a candidate for our p here. Okay, and that's what we will output. So this is polynomial time. This is this polynomial time. Okay, why is it polynomial time if it is? So it turns out that this is actually a very, very, very easy polynomial time solvable problem. Why? What am I looking for? I'm looking for coefficients of a polynomial called q. So q of x, y can be written as summation c sub jk, jl, x to the j, y to the l. Okay. I'm asking us to find the c sub j's, jl's. Okay. The constraints that I'm giving you, what kind of constraints are these? These are linear constraints in c sub jl. Okay. So this is a big linear system. We know how to solve linear systems. No problem. Gaussian elimination is good enough for us. We can solve this in polynomial time. Now we can also ask the question, why does this Q even exist? Okay, linear systems work great if the solution exists. The solution does not exist, we can't do it. Well, first remember, there was always a solution. I could have used C sub j L equal to 0 for all C sub j L. It would have satisfied all of these conditions except for this one. But that tells us that the linear system we are looking for is a homogeneous linear system. That's why all zeros is a solution. If a homogeneous linear system has fewer equations than the number of variables, there is also a non-zero solution. How many variables do we have? Well, we have square root of n plus 1 times square root of n plus 1, more than n variables, strictly more than n. How many constraints do we have? Exactly n. So this linear system always has a solution, and it's trivial to find a solution, linear algebra. Okay, now comes the second problem. Okay, so this thing, maybe in fact, we'll find many, many solutions. There's an entire, 10-dimensional space of solutions. Which one of these should I work with for the next step? Do I have to pick it carefully? And the answer is, it doesn't matter which one you work with. Take any solution to this. If this number of agreements is large, this polynomial will be a factor of q of xy. Okay, I will not prove this. It is, I'll prove a special case of this in the next lecture, special case and a variant, etc., in the next lecture. But it turns out you can actually prove that if the number of agreements is at least 2 times k times square root of n, then this y minus p of x will divide q of xy. It's not the best result that I could have hoped for, but at least if we are thinking of k as much, much, much smaller than square root of n, okay, it's rate 0, but still, k is much smaller than square root of n, this would have been good enough to solve the algorithmic problem. So it solves the problem if epsilon is less than 1 minus 2k over square root of n. Not quite what we wanted, but close enough. There are 2 or 3 very simple manipulations. 2 manipulations are very simple. One thing you say is, oh, I don't want to use degree of q and x and y is the same. So here use degree nk, and there use degree n over k. Okay, in y. If you do this, then already you will get a much better solution. It'll be 2 times square root of k over n. Now we are in business. This is positive rate regime. Okay, so we can deal with positive rate and get error correction close to 1. Now you can do even better by being even more careful about what kind of a polynomial Q you find more structural restrictions. And if we crash our heads against the wall, which is what Guruswamy and I did in '98, then you can, it's significantly more sophisticated, but you can get 1 minus square root of k over n. So what does that look like? We are saying, okay, Reed-Solomon codes actually achieve this line, this red line here, okay, or this red curve. This curve is the plot for this 1 minus square root of k over n, well, by hand, okay. So it does reach this point, it does reach that point, it will be always above this line, it's always below that line, okay. But somewhere in between. But our goal is to get closer to this thing, and this is what we will try to do next lecture, okay. All right, so next lecture, we want to get this line, and so let's stop here. And I'll be very happy to take questions for as long as people have questions. I should also mention, if people want to drop by my office hours to ask questions about either today's lecture, tomorrow's lecture, or unrelated stuff, you're welcome. Dimitri sent us the link earlier.
So thank you for the amazing lecture. So yes, I've already sent the link to Moodle's Zoom. Hopefully everybody received this email. So if there is no questions, let's stop for today.
I have a question maybe.
Yeah.
Go ahead.
I also know how to factor polynomials in one variable, but we have polynomials in 2 variables here, so in x and y. So how does factorization there even work? I'm not sure.
Great. It's a fantastic question. I wish I had a very short answer, but if you just want to get a general idea of why this should even be possible, not necessarily the best, most efficient way, here's what you can do. If I have a polynomial q of x, y, what I'm really looking for is a factor of the form y minus p of x, right? So here's what I can do. Plug in y equal to some random polynomial r of x of degree k. Okay. So what will happen is that if originally y minus p of x was a factor, now r of x minus p of x will be a factor of this new polynomial. Okay. And r of x minus p of x is with some positive probability irreducible. Okay. So you can appeal to univariate polynomial factorization, and this would. So if you know how to factor univariate polynomials, then at least you know that this should be doable in polynomial randomized time. You can actually do it deterministically and so on. Reduction to univariate is deterministic, but this is the simplest explanation I have.
Great, thanks. I think there's another question in the chat.
Great. Why a Toeplitz matrix works? Okay, good. Okay, so there's also, can you send the link again? Right, so I can send, so let me just put it here. So this is my link for all my talks, and it also has the link to the Zoom. Actually, why am I doing this? Sorry, it's right here. Okay. If anybody has trouble accessing it, let me know. Okay, good. There's a couple of other questions. Oh, why does a Toeplitz matrix work? Well, roughly, you have to go through the proof kind of carefully and see what is it that you needed from your random encoding and decoding functions in order to prove that this is a code. All you need to say is what's the probability that there exist two code words that are close to each other, or one code word which is one non-zero code word which is close to 0. So just looking at where this one code word is mapped to is good enough, and then the rest of it, the proof is a union bound. And if you multiply a non-zero vector by a Toeplitz matrix, you get a random vector. So that's roughly why Toeplitz matrices work. Any matrix, family of matrices which has the feature that if you multiply a non-zero vector by a random matrix gives you a random thing, that should give you a good error correcting code. Why Toeplitz matrix? Good. Sorry. Okay. Yeah, a Toeplitz matrix is specified by order of n random bits, and that's why I want to go with Toeplitz rather than a random matrix, which should have been order of n square. Thank you. That's probably the right answer. How would the rate versus distance curve change if we restrict ourselves to uniformly random errors, the model we discussed in the beginning? It's a great question, and I wish I had actually done it justice. For any letter of the alphabet, you can say, okay, what is the, suppose we are looking at the query symmetric error channel, okay? You can work with q equal to 2 or anything else, and then you will have something saying, okay, if you have rate here, it will vary from 0 to 1. The distance can only go up to 1 minus 1 over q. And then there will be some curve over here which says this is the rate that's achievable. Sorry, this is rate and that's error. This fraction of errors is the best that you can correct if they were random query symmetric channels. Okay, so what does it mean to be query symmetric? X gets translated as X with probability 1 minus epsilon, and it's transmitted as X prime with probability epsilon over q minus 1, where X prime is not equal to X. Okay, so for each one of the X prime not equal to X, there'll be some curve that looks like this. If you are trying to correct random errors, this is what you can do. If you want to do list decoding with epsilon fraction adversarial errors, the curve is the same. Okay, this is the same curve. Okay, so this is list decoding with adversarial errors, and that's random errors. They actually achieve exactly the same limit. The gap in our knowledge is mostly algorithmic. We are able to do a lot more with random errors because these are random errors, and a lot less with adversarial errors. Adversarial errors we are catching up. Next lecture, we will show how to do it over large alphabets and get close to the right limit. We don't know how to get it to the right curve for every q. In particular, q equal to 2, we are very, very far from it. But on the other hand, if you want to go to q equal to, q pretty large enough, then polynomial in n, for instance, then it's very, we are able to get to the right capacity limits. For random errors, we will show you 3 solutions which are easy, which will get you close to this bound, and then the 4th solution, which is which will achieve it with very, very, very strong behavior, and that will be the subject of the second half of these lectures. Yes, adversarial errors, encoding and decoding with small alphabets is major open question. There has been, like every tiny step of progress that we have seen is the beautiful results. So for example, a few years back, Tashma got one of the best paper awards, I think at the Stocker Fox or something, for discovering codes which roughly look like, they're achieving binary codes which are achieving this kind of a bound, explicit codes, but with inefficient encoding and decoding. So we are very far from that regime yet, but we are getting, we're making progress slowly, but it's not. What's the difference between adversarial and random errors? So adversarial errors, you're allowed to change an arbitrary fraction of the messages, but then because you're allowed to of the code word, because it's very malicious errors, we allow the decoder to output a list of messages. With random, you just pick every coordinate independently at random according to this thing. If that didn't answer the question, feel free to open up, ask again. Rani is asking, is list decoding of an erasure channel easier? So an erasure channel is a beautiful one also. So for example, a binary erasure channel would, if you transmit a 0, you always get a 0, though with some probability you might get an explicit question mark saying, I don't know what it is there. When you transmit a 1, again, you get a 1, but with some probability you get an explicit question mark. So you can define the same model, this model of, it's not just random model, but it's also an adversarial model. But again, an adversary is not allowed to change a 0 to a 1, only allowed to change 0s and 1s to question marks. Then you can ask the question, how well can you list decode this? Algorithmically, there is no challenge in list decoding. If you use a linear code, erasures, well, you're still getting a bunch of linear functions of the message, so you can solve a linear system to solve the problem. But there is actually very interesting probabilistic and non-algorithmic questions. What is the exact limit is not completely understood, and it leads to very interesting phenomena like trace reconstruction and so on, which people study extensively. All right, so this is a good lull. Okay, sorry, go ahead, Dmitry.
Yeah, thank you again for lecture. So let's stop for today. I'll stop the recording.